Hi, in this video I am going to discuss Edexcel IAL May June 2022 Unit 1 paper WPH1101 paper. Okay, first question MCQ. A machine has a power of 750 watts and transfers 150 kilojoules of energy during a time t. Which of the following expressions gives t in seconds? You know the equation. Energy is equal to power into time, or we can say power equal energy divided by the time. So energy we know 150 kilojoule, so 150 kilojoule to convert to joule multiply by 1000 equal power is equal to 750 watts into t. So t will be equal to 150 into 1000 divided by 750. So that expression is given answer C. Okay, question number 2. Second question MCQ. A sphere falls through a viscous liquid as shown. Diagram is given. Which row of the table describes the upthrust and viscous drag on the sphere as it accelerates downward? So it's going to fall down and accelerates. So what can you say about the upthrust? You know, upthrust is equal to weight according to Archimedes principle. Upthrust is equal to weight of the displaced fluid. Weight of the displaced fluid is constant because weight of the displaced fluid, that is upthrust, is equal to weight of the displaced fluid. Weight of the displaced fluid is equal to volume displaced by the sphere. The sphere is completely inside, wherever it stays inside the liquid, completely inside the liquid, the volume it displaces will be the same. So that is volume same. The density of the liquid into G, that is the upthrust. So upthrust will not change even when the sphere falls down. Already it is completely inside the liquid or water. Viscous liquid, yeah, not a water, it's a viscous liquid. So there's no change in upthrust. But when it moves down, it's going to accelerate. You know, the downward resultant force will be more than the downward total force will be more than the upward force, which is drag and upthrust. So it will accelerate. When it accelerates, the speed will increase or velocity will increase. When the velocity increases, the drag force, the viscous drag, according to Stokes' law, is given by, the drag force is given by 6 pi eta rv. So when it accelerates, the speed will increase, so the drag force will increase. So here no change, drag force will increase. So the correct answer B, constant and increase. So the correct answer is B for question number 2. Question number 3. Which of the following is a scalar quantity? It's just normal, very simple. You know, force has direction, momentum has direction and magnitude, force has both magnitude and direction. So scalar means that has only magnitude, no direction. The correct answer D, work, energy, they all are scalar quantities, no directions. So question number 4. The graph shows the relationship between tensile stress and tensile strain for a material. The graph is given. The graph is given like this. This is tensile stress. This is tensile strain. So you can see initially smaller portion looks like straight line, then it curves. So this is elastic limit. So this is elastic limit. And here breaking point given, right? Okay, which of the following gives the Young modulus of the material? You know that Young modulus is the gradient of stress strain graph within the linear portion. So only the linear portion. So the initial portion is given as linear portion. So within the linear portion we should find the gradient. Okay, we'll see the answers. The first answer, the area under the line up to the breaking point. No, the area under the graph for stress strain gives the energy density, that is energy per unit volume. So that is not the answer. The area under the line up to the elastic, that also energy density up to the elastic limit. So that is not the answer. Gradient of the tangent to the line at the origin, because at the origin, if it is not a perfect straight line, they didn't mention it's a straight line, but at the origin. So before just it curves at the origin, we can say that this looks like straight line small portion. Anyway, whatever it is, the initial portion, the linear portion, the gradient gives the Young modulus. So correct answer for C, question number 4 is C. The linear portion of the gradient of the linear portion gives the Young modulus. So question number 4, correct answer C. Okay, question number 5. A student determined a value for G by dropping a metal sphere from rest. The student measured the distance fallen and the time taken for the sphere to fall. The student obtained a value for G 11.2 meter per second squared. Which of the following could explain the difference between the student's value and the accepted value? We know the student got a larger value than the actual value. Actual value is, we know that, which is 9.81. So the equation we can use when the sphere is dropped, S equal ut plus half at square. If I use it, it's dropped from rest, so u will be equal to 0. So I can say S equal 0 plus half gt squared. So the value of G is equal to 2s over t squared. He would have used this equation. So he would have measured something wrong. But actually, if he measure the S correctly and T correctly, he will get the actual value 9.81. But he is getting 11.2, which is larger than the actual value. What could be the reason? The first one, the air resistance was not negligible. So air resistance was not negligible means he got a particular amount. He measured a certain amount of time. So there, if I consider the drag force, that means if the drag force is not negligible, what happened? The time what he measured is going to be larger actually. So the time what he got is larger due to the drag force, but he neglected it. So if we want to do correction for the drag force, the time value should be reduced. Now when he reduced the time value, and imagine if the measurement of S is correct, if the measurement is S is correct, and when he reduced the time value to correct the error due to drag force, you know, whenever there's drag force, the measurement of time will become larger, is it? So he neglected it. So he thinks, okay, due to the drag force, I got a wrong value, which is 11.2, and he is trying to correct it. And if he wants to correct it, the outcome of the drag force, he should reduce the time value, is it? When he reduces the time value, what will happen? The G value will become larger further. So he already got 11.2, and if we do correction for the time due to the drag force, he should reduce the time. When he reduces the time, what will happen? The value of G will become larger than 11.2. So this error is not due to the drag force, right? So statement A is not acceptable. Statement B, the student's measured distance was greater than the actual value. Okay, he measured S larger than the actual value. So what correction he can do? He should reduce the value of X to correct the actual value. He should reduce the value of S. When he reduces the value of S by keeping the measurement of time correct, but he got his correct time value, but only thing he need to reduce the value of S, then now he got 11.2 for the G. That will become smaller when he reduces the value of S. So the mistake here is measurement S is wrong. He measured a larger value than the actual value, so he should correct it. That means he should again measure it, which should become smaller than the earlier value. Then the G value will become smaller than 11.2, which could be 9.81. So the correct answer is B. Question number 5, correct answer is B. Okay, we'll check the other two answers also. The answer C, the sphere did not fall vertically. So actually, when he dropped, the sphere would have gone at an angle, maybe something like the projectile it would have gone, but he assumed it fallen vertically. He assumed it fell vertically, but actually it moved on an angle. So what correction should he do? So he took actual distance is this much. He thought it's falling vertically, means the distance it's fallen is larger than the vertical distance. So what correction should he do? He should increase the value of S to do the correction, because actually it fallen this way. He assumed it's falling vertically. If that is the error, he should increase the value of S when he do the correction. So there, when he increases the value of S, the G value will become larger than 11.2. So that is not the mistake. Okay. Then answer C is also not acceptable. Answer D, the student's measured time was greater than the actual time. So if he thought, okay, I measured the time larger than the actual value, the correction, what should he do? He should reduce the time, what he measured, maybe a certain value. He should take a smaller than that time. Then what will happen when they reduce the time, G value will increase, then that also will become more than 11.2. So he got 11.2, which is larger than 9.81, is only due to the measurement S becomes larger. That is the mistake. So he should reduce the measurement of S. So correct answer is B. Okay, question number 6. A rocket is accelerating horizontally due to a constant resultant force. Resultant force is constant. The mass of the rocket decreases steadily as it used up fuel, right? The mass is decreasing uniformly. So which graph shows how the acceleration of the rocket could change? Okay, so here we don't need to try to get an equation. We know that the resultant force F equal ma, right? So force is constant. So the resultant force is constant. If the resultant force constant and if the mass also remains constant, then the acceleration will remain constant. Then the graph will be a horizontal line. When the time passes, if there is no change in mass, no change in F, acceleration will be constant. So throughout the motion, the acceleration will remain constant. Then the graph will be a horizontal line. But what's happening here? The mass is decreasing uniformly with time. So when time passes, mass is decreasing uniformly, force is remaining constant means force is remaining constant, mass is decreasing uniformly means we know that acceleration should increase. So acceleration should increase means here the four answers are very simple. They are giving only one graph such that the acceleration is increasing. So the correct answer is B. All other answers, A, acceleration kept constant, that can't be because mass is decreasing, force is constant. So acceleration can't remain constant. Answer B, yes, where that's the only graph where acceleration is increasing. Answer C and D, both acceleration is decreasing. Acceleration won't decrease for a constant force when mass decreases. So the correct answer B for question number 6. Okay, question number 7. Two arrangements P and Q of identical springs, so that means they have same spring constant K, are subjected to the same tensile force F as shown. When one spring is subjected to a tensile force F, the elastic strain energy for the spring is E. So you know one spring is subjected to force F, the elastic strain is E means we know that for that one spring, I can say for one spring, I can say E is equal to half K delta X squared. Half K delta X squared for one spring. Okay. Which row of the table gives the total elastic strain energy for each arrangement? So here two springs are connected in series. Here two springs are connected in parallel. Right? So what would be the total energy in this system and this system? Okay, so here the force F is acting on both springs because they are connected next to next. You know, if you think about the Newton's third law, say for example, if the force here F means the force acting on this spring is F, the force acting on this spring is also, if you think about the free body force diagram, if I break it here, right, if I draw this diagram like this, break it here and draw again like this. So here this force F is acting to balance this one, there should be force F. This force should be given by the first spring. So first spring exert force F on the second spring on diagram P. So second spring exert the same force F on the first spring. So to balance it, here should be F. So the tension here is F, tension here is F. So both spring or each of the springs will have force which is equal to F. So there each spring has the same force F. So if I consider the energy stored on one spring of here will be E is equal to, for one of the springs I can say the first spring, this is the second spring. For the first spring under P, for first spring if I consider the same extension it will have, because same force is acting, F equal K delta X. If I think about it, same extension both will have, which is equal to delta X. So the energy is going to be half K delta X squared for the first spring. For the second spring also, the energy E will be equal to half K delta X squared. So the total energy will be equal to half K delta X squared plus half K delta X squared, that will be 2E. So the total energy on the system P will be equal to 2E. Right. Now when I think about diagram Q, what happens? This force F will be divided equally. See, think about about free body force. If I draw this spring Q like this, and this spring, the second spring also like this, and this rod here, F, for the equilibrium of this rod, it should have a force this direction, F. So this F will be equally divided, here F by 2, F by 2. So here there should be F by 2, here also F by 2. So the tension on each spring will be F by 2 on the diagram Q. So the tension F by 2 means, according to Hooke's law, F equal K delta X. F by 2 is equal to K into delta X by 2. Each spring have extension same, which is delta X by 2. So energy stored in one spring will be equal to E1, if I say half K. The extension will be delta X by 2 all things squared. So it's going to be half K delta X squared into 1 over 4. That is 1/4 of E, because E is half K delta X squared. So both springs together, total energy, when the two springs are connected in parallel, total energy will be 1/4 of E plus 1/4 of E. That is will be E by 2. So in this system, total energy stored E by 2. In this system, total energy stored is 2E. So for P 2E and Q E by 2, the correct answer D. Question number 7, answer D. Or you can use half F delta X for the question 7, like this. So question 7 again I'll do with half F delta X. Either way you can use half F delta X or half K delta X squared. You will get the same answer. So when one spring is when a force of F is applied to one spring, energy stored in it will be half F delta X. Okay. Now on diagram P, I already explained, each spring will have the same force F. So there on P, on diagram P, the total force will be equal to, the first spring will have the same force F, the extension will be delta X. Second spring also half F delta X. So half F delta X means that is E plus E, that is going to be 2E. Now when you think about Q, I told already, each spring will have force F by 2. The parallel springs, each of them will have force, the tension will be F by 2. When the force acting on it becomes F by 2, each spring will have extension half the early extension. One spring, when it's subjected to a force F, if its extension is delta X, when the same spring has tension F by 2, then the extension will be half of it, because force becomes half, so the extension also will become half. So here on diagram Q, each spring will have extension delta X by 2, and since each springs have tension F by 2. So there on Q, the total energy will be, if I use half F delta X, half, the force is going to be F by 2 for the first spring. Its extension will be delta X by 2. Again, the second spring, half F by 2 into delta X by 2. So it's going to be 1/4 of half F delta X. 2 into 2, 4. I took it outside. 1/4 of half F delta X plus again 1/4 of half F delta X. So half F delta X is E. So 1/4 of E plus 1/4 of E. That's going to be half E. So here also you can see, if you follow this equation, half F delta X also, you will get the same answer, the correct answer, D. Okay, question number 8. This graph is given velocity time graph. Velocity time graph shows the motion of a particle with a constant acceleration. PQR represents the magnitude of each area shown. So this area is P. So this area is P. Sorry, Q. This area is Q. And this area, so the upper area, I think up to here, they didn't put a line, that is P. And this triangle, the area of this triangle is R. Okay, the area of that triangle is R. Okay, so which of the following expressions give the total displacement of the particle? So students normally ask why the velocity is starting with a negative quantity. Okay, so I can say like this. Imagine we take this direction positive, this direction we take positive. When you are considering a vector, we can take any direction positive. So we would have taken this direction positive when we take an object, say maybe a vehicle or whatever. An object has an initial velocity this direction, maybe u, at t equals 0. So the velocity is towards left, which is opposite to the direction we took positive, right? So the velocity initially is going to be negative. Then what's happening? It's decelerating. It's decelerating from here at time t1. I'll mark this value t1, this value t2, right? So when the time becomes t1, at t equal t1, it has come to rest. You can see the velocity is 0 here. So at time t equal t1, the object has come to 0, the rest, momentarily rest. Then what's happening? It's accelerating in opposite direction. So that you can see the velocity is positive here. Here the velocity is negative, which is below 0. So it's decelerating. Initially when t equals 0, it has velocity towards left. I took velocity towards right, positive. So initial velocity is negative, but it's decelerating uniformly and comes to rest at time t equal t1 at this point. Then what's happening? It's accelerating in opposite direction. That means its acceleration and the deceleration has the same magnitude, right? The acceleration and deceleration has same magnitude. So it's accelerating in opposite direction. So when it is accelerating in opposite direction, it's uniformly accelerating and moving a larger value. You can see the displacement it has moved under the area R, area covered by the graph, and the time axis gives the displacement. This area is larger than this area. When you consider this triangle, that smaller area, this is large area. So this displacement is smaller. Now it's accelerating towards right. It's accelerating towards right. Maybe at time t equal t2, it would have gone from here to here. So at time t equal t2, it has gone up to this point. So what is the displacement during this journey? What is the displacement during this journey means? That is going to be this one. This is the displacement during this journey. From the initial point, we should consider the final point towards right. Okay, so how do you find this length? This length, from this length, I should subtract this length. This length is the area R. This is the area R. From here to here is the area R. From here to here is the area Q. So the displacement, that's a question, following which of the following expressions gives the total displacement of the particle, means total displacement will be R minus Q, or R minus Q. That is answer D. For the same graph, I can give another example. Imagine a ball is thrown from edge of a cliff. Maybe this is the cliff. From edge of a cliff. The height of the cliff, we can take it as R, or whatever it is. A ball is thrown from the edge of the cliff. So if the ball is thrown from the edge of the cliff at a particular velocity in upward direction, it moved upward direction, reaches the highest point where the velocity becomes 0, then it moves downwards to the ground. Okay, so here from the edge of the cliff it went up to a height. That height, up when it reaches the highest point, its velocity becomes 0. We know when it moves from here to here, it will decelerate. So there, if I take downward direction positive, initial velocity u is upward direction, it's going to be negative. So the graph will start with a negative quantity. When it moves upwards, it's going to decelerate. So the velocity will decrease. At the highest point, the velocity is 0. Then from the highest point, it's going to fall down and accelerate. The velocity is downward direction. It's along the direction I took positive, so the velocity is becoming positive. When it moves upwards, its deceleration is deceleration is 9.81, or I can say its acceleration is minus 9.8. When it falls down, it's accelerating again downwards at 9.81. Okay, so there it moved up, then moved down with the same magnitude. Here it decelerates, then it accelerates. Okay, so there what happened? The height it moved from the edge of the cliff to the highest point is given by this area, which is Q. The distance is fallen from the highest point to the ground is given by this area covered by this triangle, that is R. So what's the total displacement in this motion? The total displacement initially here, finally here, this is going to be the total displacement. That is going to be, total displacement S is going to be R minus Q. So here also, in this example also, I can say the final answer D. Okay, question number 9. A cyclist rode along a slope at constant speed. So constant speed means no gain in kinetic energy, no change in kinetic energy. So constant speed. The increase in vertical height of the cyclist was delta h, shown on the diagram. The slope was at an angle theta to the horizontal as shown, right? The forward force of the road on the bicycle was F and air resistance was negligible. Which of the following gives the work done by the cyclist? Okay. Sometimes students get confused, but we can answer this in two different ways. There's a forward force on the cyclist, which is F. So you know the cycle wheel rotates. So the wheel will push the road back. Road will push the wheel forward according to Newton's third law. That is the F. So actually that force should be given by the cyclist. So cyclist also giving the same force on the pedals, right? So the forward force is F. So the cyclist is moving along the slope a distance d. We'll take it like this, and the angle is theta. You know, the question is which of the following is the work done by the cyclist? So method 1, I can say work done by the cyclist is equal to force into distance moved along the direction of force. So the force is applied on the bicycle wheel along the slope upwards. So the distance moved along the slope, I took it d. So work done by the cyclist is equal to force into distance moved. So d is an unknown, so I need to eliminate the d in terms of the given quantity. So you know that sine theta is equal to opposite delta h over d. So d is equal to delta h over sine theta. So substitute this d in this equation. So the work done is equal to force into delta h over sine theta. So the correct answer, F into delta h over sine theta, the correct answer D. This is method 1. Okay, method 2 if I follow. He's moving at constant velocity. So he's moving at constant velocity means I can say work done by the cyclist. The drag force is negligible. So no work done against drag force. No gain in kinetic energy because constant speed. So I can use the equation work done by the cyclist is equal to gain in gravitational potential energy. That way also I can say work done by the cyclist is equal to gain in GPE, gravitational potential energy. So work done by the cyclist, I need to get an expression. Gain in GPE means mgh. Okay, so nothing is mentioned about mass. How can I eliminate m? We know the cyclist is moving at constant velocity along the slope upwards means the component of the total, so m is the total mass of the cyclist at the cycle. Total mass of the cyclist and the cycle. The cyclist moving upward along the slope at constant velocity means, constant speed means there should be a force acting downwards, the component of the total weight of the cyclist and the cycle, which is mg sine theta. So since he is moving at constant speed, mg sine theta must be equal to f. These are the only two forces acting along the slope on the cycle. Upward direction on the wheel F due to the contact force between the tire and the slope. The component of the weight along the total weight, I consider the weight of the cyclist and the cycle together, along the slope downward mg sine theta. So I should say F must be equal to mg sine theta. So I can say but F must be equal to mg sine theta. So I can say mg is equal to F over sine theta. Gain in GPE, mg into height moved. So gain in GPE is equal to, so work done, I'll continue here. Work done is equal to gain in GPE. So that is mg delta h. Mg, I got an expression F over sine theta into delta h. That is F delta h over sine theta. If you do this way also, you'll get the same answer, which is the, anyway, you can do either way, you'll get the same answer. Okay, question number 10, it's an interesting question. When compressed by a force of 50 Newton, a spring had a length of 12 centimeters. So they are not telling the compression, they are not telling anything about the initial length. We'll see. So imagine, we'll think this way, question number 10. Initially the length of the spring is L0, natural length is L0, right? We'll think like this, the natural length is L0. Okay, when you compress it by using a force of 50 Newton, means both sides you should give the same force. Students have confusion. They think one side if we give 50 Newton, that's enough. No, both side is the compression. Say for example, if you have a spring hanging like this, and if you are applying a force of 20 Newton here, the force acting here also upward direction 20 Newton. If you think about the free body force diagram for this one, here 20 Newton. If this is the only force acting on it, it would have fallen, but it's not falling down. So there should be a force upward direction 20 Newton to keep it at rest with extension. So this 20 Newton is given by the roof or where you are hanging it. So the roof also will have the same force, these two are Newton's third law pair. So you can see when a spring is extended on either side, the same force acts. Same way when you compress a spring on either side, the same force should act. You can't mark the force only on one side. Both sides should be marked whenever there is a compression or extension. Okay, so here initially the natural length of the spring is L0 when there is no force acting on it. Now we are compressing it with a force of 50 Newton. The length of the spring has become 12 centimeters. So now we'll draw like this. So maybe a little longer. So you are applying a compressive force of 50 Newton. So compressive force of 50 Newton either side I should mark. The length has become 12 centimeter. Now when you apply force of 70 Newton, it has become now 7.1 centimeter. Okay, the question is, what could be the expression for spring constant K? Okay, so here I can write the natural length is L0. So here the compression delta X will be L0 minus 12 in centimeter, Newton per centimeter. They are asking to find the K in Newton per centimeter. So I don't need to convert centimeter to meter. So here delta X1 is L0 minus 12. Here the delta X2 when the force 70 Newton acts is L0 minus 7.1 centimeter. Okay, so for this I can use the equation Hooke's law, F equal K delta X. If I write here, 50 is equal to K into delta X is L0 minus 12, equation 1. Here if I write the force F is 70 Newton is equal to K into L0 minus 7.1, second equation. Okay, that's all. I need to find an expression for K. Right. We'll subtract. So before subtracting, multiply it inside first equation. So there you will get 50 is equal to K L0 minus 12. K, make that equation 1 rather than this. Here also multiply inside, 70 is equal to K L0 minus 7.1 K. Keep it second equation. Okay, right. So now subtract second equation minus first equation. 70 minus 50. KL0 will get cancelled. Minus 7.1 minus because I am subtracting 2 minus 1. Second equation minus first equation. So from minus 7.1 if I subtract minus 12.k, it will become 12.k minus 7.1k. So this can be, I can write this as 12 minus 7.1. Take the k outside. Make the k subject. K equals 70 minus 50 over 12 minus 7.5. That's answer. Which answer? That is answer B. The correct answer, B. Minus 7.1, sorry, 7.1. Okay, question 11, a disc of mass M, section B, question number 11. A disc of mass M is held stationary by a force F exerted by a magnetic base as shown. So there's a drawn diagram given. A disc is floating about a magnet. The free body force diagram for the disc is shown below. Upward force F and downwards weight mg are given. The two forces shown are equal in magnitude and opposite in direction. Give two reasons why these forces are not Newton's third law pair of forces. You know the condition. If they want to be Newton's third law pair, they should have the same magnitude. Here they have the same magnitude. Okay. They should act in opposite direction. Here also they are acting in opposite direction. So you can't tell them. Third condition. they should be the same type of forces. Newton's third law pair of forces are always same type. That means here mg is weight, which is a gravitational force, F is a magnetic force. They are not the same type, so they can't be Newton's third law pair of forces. So first you can say they are not the same type of forces. F is a magnetic force or electromagnetic force. Mg is a gravitational force. First reason you can say. The next thing, they should always act on two different objects. Newton's third law pair of forces always act on two different objects, but here they are acting on the same object, therefore they can't be the Newton's third law pair of forces. So you can say those two reasons, you say they are not the Newton's third law pair of forces. That is the answer for question number 11A part. Question number 11B part, the magnetic base has weight W and rests on a horizontal table. Complete the free body force diagram below for the magnetic base. So they are giving a magnetic base, B part, is resting on a table. What are the forces acting on it? W is given already, that is the weight of the magnetic base. Then you need to draw two more forces. One is the third law pair of the force given by the disc. Disc is pushed upward direction by the magnetic base. So according to Newton's third law, this will push the magnetic base downwards. That you can mark with force F because they already showed F for the disc. So you can draw downwards F, then the normal reaction exerted by the table. So the length of the normal reaction should be taller than or longer than these two, because that should be equal to the normal reaction. R must be equal to W plus F. So if you add these two lengths, that must be equal to R. You can say R normal reaction. So that should be longer than these two lines. Okay, question number 12. When an increasing force is applied to a steel cable, it will eventually reach its elastic limit. A part, state what is meant by elastic limit. Okay, you can say either way. You can say the limit of force up to which the material will extend, and when the applied force is removed, it will return to the initial shape or original shape. The maximum limit of force up to which the material will extend, and when the applied force is removed, it will return to the original shape. You can say either that way, or you can say beyond this limit of force, when the applied force is removed, it will not return to the original shape. Beyond this limit of force, when the applied force is removed, when the material will not return to the original shape or initial length. Either way you can say. Students have confusion about elastic limit and limit of proportionality. Limit of proportionality means the limit of force, or up to this limit of force, the material obeys Hooke's law. That is the limit of proportionality. This is elastic limit. So elastic limit, I already gave the answer. Question number 12A part, answer is given. Question number 12B part, the elastic limit of the steel cable was reached when the force of 13.4 10 to the power 6 Newton was applied. The extension of the cable is given 0.126. Length of the cable, that's the initial length, also given 6 meters. Cross-sectional area given. Calculate the strain of the cable. So it's a direct application, nothing harder. So question number 12, B part, A part, B part, first part. So strain, they are asking, calculate the strain. You know strain is equal to, this is the symbol for strain, extension over original length. So extension is given, that is 0.126. Original length is given 6. So that is going to be 0.021, no unit. Second part, calculate the stress. Calculate the stress of the cable at the elastic limit. Stress is equal to force over area. So stress is equal to applied force on the, that is tensile force over area of cross section. So that is 13.4 10 to the power 6 Newton divided by the area of cross section given 9.60, 10 to the power minus 3 meters squared. So that's going to be 1.40, 10 to the power 9 Newton per meter squared or Pascal. Either way you can given strain. Okay, so question number 13 on force. A coat hook is attached to a smooth door by a screw as shown. A photograph is given. The diagram below shows three of the forces that act on a coat hook when a coat is hung from it. The weight of the coat hook may be neglected. So there are two forces are given: horizontal force from the screw and the weight. Add a labeled arrow to the diagram to show the additional force required for the coat hook to be in equilibrium. So when you are marking the third force careful, you should know that when object is at rest or equilibrium under 3 or more than 3 non-parallel forces, they all must be on the same plane. First condition, they all must meet at one point. So for example, I can show a good example, not related to this question, but condition for an object which is at rest under more than 3 forces, right? They are among them non-parallel, but they are acting on the same plane. How should they act? Say for example, on a rough wall, on rough ground, a ladder or a rod is kept at rest. Both are rough. So both are rough surfaces. Okay. So how should the forces act? How many forces are acting? On the floor, the rod will try to slip to the right. So there will be a friction towards left on the rod. So there will be a friction towards left here, Fr. There will be a normal reaction from the floor. Normal reaction, call it R1. This is friction, call it Fr. Then there will be a normal reaction from the wall, that let it be R2. And you know the rod is going to slip downward, so there will be a friction, that is F-R, upward direction. Then what else? The weight of the rod. So there are 5 forces acting on the rod. At the bottom, friction and normal reaction. Where it touches the wall, a normal reaction and the friction and weight. Now there are 5 forces. Weight. Where should I mark the weight? The rod might be a non-uniform rod. Okay, how should it act? Now there are 5 forces. 1, 2, 3, 4, and including the weight, there are 5 forces. All these 5 should meet at one point. But we can reduce these 5 forces into 3 forces simply. How can I reduce these 5 forces to 3 forces? Now these two can have a resultant. Fr and R1 will have a resultant. So that resultant may be along this way. The resultant of these two may be acting along this direction. Let it be F1. The resultant of these two also might be acting this direction. This is the resultant of these two. Let it be F1. Resultant of these two will act along this direction, F2. Then along this point, through this point, where the resultant of these two acting F1, resultant of these two acting along this direction, they meet at one point. So that through that point, the line of action of the weight should act. The weight should act along that line of action. Now I converted these 5 forces into 3 forces. The resultant of these two, resultant of these two, F2, and the weight should pass through where the F1 and F2 intersect. Like that, you can come across many forces, but they are non-parallel. They are not parallel among them, but they should be on the same plane. So they all must meet at one point. You can reduce the number of forces into 3, like what I showed. They all must meet at one point. So by using this idea, consider this idea to answer this question number 13. The diagram what I drew, I just took an example to show how to draw a diagram where more than 3 non-parallel forces act. Nothing related to question 13, right? Now I'm going to question number 13. There a diagram is given like this. This is the hook, diagram of the hook. So there horizontal force by the nail is given, force by screw. I write shortly. And there they are giving the weight of the coat is this way, weight of the coat. Okay, so at the labeled arrow, the diagram to show the additional force required for the coat hook to be in equilibrium. Okay, so the hook is kept on the door. So door is going to touch the hook. Door will exert a force, push. Where will it act? You know, these two forces will meet at one point. One minute. So here, these two forces, so it should be like this. The coat, now look at it. These two forces will meet at one point. Through that, the contact force can't act. So I can say like this. The force given by the wall should act somewhere here. The force given by the door. The push by the door should act somewhere here. Like this. Push by door. So these two forces will meet. There's one more force given here, vertical force from the screw. I forgot to draw that. Vertical force from the screw also given here. Vertical force from the screw also given. Right. So now what happens? There are four forces. Weight of the coat, push from the door, force by the screw in horizontal direction. This is horizontal force by the screw. And vertical force by the screw. Okay, so these two forces will meet at one point. So through this point, the resultant of these two will act. The resultant of these two will act. So they can act here. The resultant of these two, vertical force of the screw and the horizontal force of the screw will act here. The weight of the coat is acting down. So the push by the door should act somewhere here. You can't mark this one. Most of the students, they mark it here. They mark this force, what I drew by blue color ink, push by the door, they mark it here. That is wrong, because if you mark it here, the three forces will not meet at one point. Okay, so the force given by the door on the hook should act lower than this force. Then only the resultant of these two will pass through the resultant of these two. So the answer, you don't need to draw this, I just drew this to explain it. So the force should be this way. Okay, so B part, calculation. So they are saying the weight of the hook is negligible. If too many coats are hung on the coat hook, the hook will rotate and pull the screw out of the door. Point P is the position of the pivot. So that's the point where you can see the photograph. That's the point where it touches the door, right? So screw, it's giving, already I explained, a horizontal push and a vertical force. So the point where it touches the door also give a normal reaction. So that point is taken as P. The maximum horizontal force from the screw is 150 Newton. Mass of one coat is 2.6 kilogram. Deduce whether a person could hang more than two of these coats from the hook. Okay, so actually a question related to turning effect moments. We will take moment about P. The weight of the hook is negligible. So the total downwards weight is the weight of a hook, so it's due to the total weight of the codes, right? So what weight of a coat is 2.6 into 9.81. We'll take the number of coats that could be hung is n. So the total downward weight due to n number of coats is n into 2.6 is the mass into g 9.81. The length is given from the P, from the pivot P to the weight, total horizontal distance given 2.5 centimeters. From P to the screw, the vertical height also given 0.9 centimeter. We'll take moment about P, right? So we'll take moment about P. Okay, so this force, which is 150 Newton, is the maximum force, will provide a clockwise moment. You know, according to the principle of moments, the total clockwise moment must be equal to total anti-clockwise moment. So about P, this force will provide a clockwise moment. This force, the total weight of the coats, will provide anti-clockwise moment. Both should balance each other if the hook wants to be at rest. So that is 150 into, that's a clockwise moment, into distance 0.9 centimeter. I can keep it in centimeter because this is also in centimeter. 0.9 must be equal to, that's the total clockwise moment. Total anti-clockwise moment, 2.6 into 9.81 n. N is the number of coats, into the vertical distance to the line of action of force from P is 2.5. So this is the maximum force. What could be the maximum value of n? We are going to find it. So solve it, you will get n is equal to 2.11. So number of coats cannot be fraction. So the maximum number of coats should be 2. So he can't hang more than 2. Okay, question number 14. A regenerative braking system allows an electric car to use its kinetic energy to charge a battery as the car decelerates. A car traveling at 13 meters per second decelerated to rest. The energy transferred to the car's battery during the deceleration is 73.9 kilojoules. Calculate the efficiency of the regenerative braking system, mass of the car. So given, so that's the question number 14A part. So I need to find the efficiency of the regenerative system. So loss in kinetic energy, we'll find it. So loss in kinetic energy of the car, how much it loses during the braking, half m u squared minus half m v squared. So half into mass of the car is given as 1560. It was traveling at a speed of 13 meters per second. Minus, finally it comes to rest. So final kinetic energy is 0. So that's going to be 1.32 10 to the power 5 joules. So efficiency, so it's not giving all this loss in kinetic energy in the form of regenerative energy. Only it's giving 73.9 kilojoules. So efficiency in this braking system, so that is means 73.9 into 1000, convert kilojoule to joule, divided by 1.32. That's a loss in kinetic energy. So all energy is not converted to regenerative energy into 100%. So it's going to be just 56%. Okay, question number 14B part, first part. Drag force act on the car as it moves through the air. State how the drag forces vary with the velocity. You know that. Just one more question. When the velocity or the speed of the car increases, drag force also will increase. That's the answer for B part, first part. B part, second part. The graph shows how the efficiency of the regenerative braking system depends upon the initial velocity of the car for initial velocities in the range from 20 meter per second to 40 meter per second. Say earlier calculation we did for 13 meter per second, efficiency we found 56%. Now when the speed of the car initially 20 to 40, one of in that range, when it changes, how the efficiency change. So there the graph is given, which is decreasing graph. The efficiency against the initial speed. This is the efficiency against initial speed. The graph is a decreasing graph like this. Explain why the efficiency of the regenerative braking system varies as shown. You know, already we told that in the B part, first part, when the speed increases, drag force will increase. So that means drag force increases means here the equation, the energy equation we can write. Loss in kinetic energy is equal to, so the car is losing the kinetic energy during braking. So loss in kinetic energy can be converted to fully to the regenerative system if there is no drag force. But the problem is there will be drag force, so there will be work done against drag force also. So loss in kinetic energy equal to work done against drag force plus energy stored or energy given, energy stored in regenerative system, or I can say energy stored in the form of energy generated by braking system, or energy generated by as regenerative system. So here what's the problem here? When the car travels at higher speed, this quantity also will increase. So the loss in kinetic is going to be shared among two different quantities. When the initial kinetic energy is larger, when the car is traveling at higher speed just before braking, the work done against drag force during the braking, work done against drag force also will increase. So what will happen? The energy given in the form of regenerative system will become smaller. So there we can say when the car travels at higher speed and when it brakes, it will lose large amount of kinetic energy. That's true. But at the same time, what happens? The work done against drag force also will increase. Only the balance energy, which is smaller, will become regenerative energy. Therefore, the efficiency will become smaller. This is becoming larger. This also becoming larger. So this becomes smaller. Comparatively, this becomes smaller. So when you divide this by larger value, initial kinetic energy, the efficiency will become smaller. Okay, so that's the reason the graph is going down. Okay, so question 15 is related to Galilean thermometer. Before starting it, that question based on upthrust, buoyancy effect, upthrust and the weight. Okay, so before starting that question, you must know these things. That means, you know, upthrust is equal to weight of the displaced fluid. And when something is kept inside of a liquid, so imagine this is the liquid. Now you keep some object inside the liquid and release it. So you are keeping an object inside the liquid and you are releasing your hand. What happens? So there will be two forces act when you release it. So the weight and the upthrust. If the weight is greater than upthrust, what will happen? The object will sink to the bottom of the liquid. Is it? If the weight is greater than upthrust, the object will sink into the liquid further inside. If the upthrust is larger than weight, what will happen? Object will move upwards until the upthrust becomes equal to the weight. If the upthrust is greater than the object, weight of the object, what will happen? The object will move up. When the object moves up until it comes out of the surface of the liquid, the upthrust will be greater than weight. But when the object comes out of the partially out of the liquid, the upthrust depends on the weight of the displaced fluid. So what happens when the object comes something like this? It comes partially out of the fluid, something like this, means the upthrust will be only due to the part of the object inside the liquid. So the upthrust will be only due to this part. So the volume displaced by the object, the volume of the liquid displaced by the object will become smaller. Upthrust is given by volume of the liquid displaced by the object into density of the liquid into J. So here the volume of the liquid displaced by the object is only this part. So when this magnitude becomes equal to weight, it will partially float. Understand? It will partially float. But if the weight of the object and the upthrust are same, what will happen? Wherever you keep it, it will stay at that position. If the weight is equal to upthrust, wherever you keep it, at that point it will float. It will not go down, it won't go up. It will stay at that position. So remember these two conditions. When the weight becomes greater than mg, the object will move down until it touches the bottom of the liquid. If the upthrust is greater than weight, what will happen? The object will partially come out and part of the object will be outside the surface of the liquid. So the upthrust will be only due to the portion or the volume inside the liquid. So that will be smaller than the upthrust here, will be smaller than here. So that upthrust can balance the weight. If the weight of the object is equal to upthrust, wherever you keep it, it will stay there. So this question is also based on that idea. It's a Galilean thermometer. So there are different glass bulbs. You can see from the top, if you see, there are bulbs partially outside the liquid surface. Partially outside the liquid. So they are saying, first we'll read the question. A Galilean thermometer consists of a closed glass cylinder containing a liquid. In the liquid there are several identical sealed glass bulbs as shown. Attached to the bulb is a metal disc labeled with temperature. Each disc has different mass. So they are saying initially glass cylinder containing a liquid. In the liquid there are several identical sealed glass bulbs. So that means all glass bulbs have same weight, same volume, right? Identical. But the discs are attached to them. So discs are carrying the temperature indicated by the temperature. They have different weights. Okay, so as the temperature increases, the density of the liquid decreases. This can cause the bulbs to move within the liquid. So question is just 6-mark question. Explain why the particular bulb will float until the temperature of the liquid exceeds a certain value. So what happens in this thermometer? How do we use this thermometer? How to take the temperature by using this thermometer? So here what happens? There are certain bulbs have gone down. They have sunk to the bottom of the cylinder. So we don't consider them. There are certain bulbs, they are partially floating. You can see that 26 degrees Celsius, even 25 degrees Celsius, they are partially floating. But 24 degrees Celsius is completely inside the liquid and it's floating. So the temperature that should be recorded in this diagram is the temperature of the environment or the temperature of the liquid is 24 degrees Celsius. So what happens here? When the temperature increases, the density of the liquid will decrease. When the temperature increases, density of the liquid will decrease. When the density decreases, what will happen? The upthrust will decrease. So the total weight of including the bulb and the disc together, the total weight will be different for different set of bulb and the disc. So the those are marked with higher temperature have lower total weight. Lower total weight. So what happens initially, say for example, when you consider 23 degrees Celsius or 22 degrees Celsius bulb and the disc with 26 degrees Celsius, the total weight of the 22 degrees Celsius disc marked with 22 degrees Celsius and the bulb, that total weight is more than the total weight of the 26 degrees Celsius disc and the bulb. Okay, so what happens when the temperature increases? Say for example, when the temperature becomes 22 degrees Celsius, the upthrust will become smaller because the density of the liquid becomes smaller. So upthrust will become smaller than total weight of the 22 degrees Celsius. So it will sink down. But the total weight of the bulb and the disc, which marked with 26 degrees Celsius, is lower. So still it is floating partially outside the liquid level. But when the temperature becomes 26 degrees Celsius, what happens? The total weight of the bulb and the disc, which marked with 26 degrees Celsius, will become equal to upthrust. So it will go slightly further down and float. But if it becomes more than 26 degrees Celsius, upthrust will become smaller than total weight. So that also will move down. That's the principle they are using it. So here the reading is 24 degrees Celsius. We should take we can see that 26 degrees Celsius, 25 degrees Celsius, they are partially floating. So their weight is much lower at this temperature. So that's the reason upthrust is more, they are partially floating as I explained here. But 24 degrees Celsius is completely inside the liquid and floating. But if the temperature becomes slightly more than 24, maybe 24.5 or something like that, what will happen? The 24 degrees Celsius, this also will sink to the bottom because the weight will become more than upthrust. So the idea is when the density decreases, density of the liquid decreases, so upthrust will decrease, right? So that's the idea. So here we have to explain like this. First we should say what is based on Archimedes principle. We can say upthrust is equal to weight of the displaced liquid, which is given by V rho G, where V is the volume of the displaced liquid, rho is the density of the liquid, and G is the gravitational acceleration. When the weight of the disk, total weight of the disk and the bulb is greater than the upthrust, the bulb will partially float outside the surface of the liquid. When the temperature of the liquid increases, density of the liquid will decrease, but the total weight of any of the given bulb and the disc will remain constant. They have different weights, but that will remain constant. When the temperature increases, what happens? The density of the liquid will decrease, so the upthrust will decrease. When the upthrust decreases, the weight becomes greater than the upthrust, so the disc will have a downward resultant force and it will accelerate down and it will sink. That's the answer we should give. Here they are not asking how to take the reading of the from the Galilean thermometer, why it sinks at different temperature. So that's the answer. Okay, question number 16. A student is flying a kite. The kite is held in equilibrium by a string as shown. The weight of the kite is 24 Newton and the wind exerts a force of 70 Newton at an angle 43 to the vertical. So they are giving a diagram like this is the kite So 24 Newton acting vertically downwards, and with the vertical there's a force by the wind which is 70 Newton that make an angle of 43 degree. And the question is, determine the magnitude of the tension. So the string should give a tension somewhere here. That means the resultant of these two must be equal to the tension, because it's at rest, equilibrium. So when you draw a vector triangle, vector polygon, vector triangle, you should get a closed triangle. So that means the resultant of these two must be equal to the tension, right? Because it's at rest. Already three forces, they all should meet at one point, they all should be on the same plane, right? Determine the magnitude of the tension in the string by using a scale diagram. So I use a scale. You can draw it. So I use a scale. 5 Newton is equal to 1 centimeter. So 24 Newton will be equal to 4.8 centimeter, and 70 Newton will be equal to 14 centimeter. Okay, so we can draw first the vertical line. That's equal to, easy to draw. So you can measure and draw a vertical line by using a ruler which indicates 24 Newton. That should be, you should draw 4.8 centimeter length. Right. Then from there you should continue the 14 centimeter. So that is this angle. So you know with the vertical line it makes a 43 degree. So measure 43 degree from this vertical line by using a protractor and draw a line of, this is 43 degree, you should measure and get it by using a protractor. So draw a line of length for by using a ruler which is 14 centimeter. That indicates the force exerted by the wind. So the third force is the tension. So that must be from, connect these two lines, that will be the tension. Measure this length. After drawing it, measure that length. You will get, the length is 11 centimeter. I got it. The length I got 11 centimeter. So 11 centimeter, 1 centimeter 5 Newton means 11 centimeter. The tension is equal to 55 Newton. And if you want, you can give the angle with the vertical line. Measure this angle. I got 60 degree. That is the question number 16A part. We asked to find the tension by using vector diagram. Okay, question number 16B part. The student wants to determine the tension T in the string. She attaches a mass holder to the string. The student adds known masses to the mass holder until the kite is in equilibrium and part of the string becomes horizontal as shown. So the diagram is given. The student takes a photograph of the arrangement. Describe how the student can use the photograph to determine the tension T. Okay, so actually the photograph we will see like this. This is the weight hold. There will be a weight. The attached mass is there. If the attached mass is M, the weight will be mg. So this is the string. There will be tension this direction. And there will be horizontal. The same tension will be there. There will be same string. So you need to find the tension of the string. So this angle, you can measure it from the photograph by using a protractor. So by using a protractor, measure the angle theta. Then you know the tension is T, we are going to calculate it. The mass attached, you can count it from the how many slots are there. So you know the total mass you attached. So the total force acting downwards will be equal to mg. Multiply the mass by the 9.81. Then it's simple. I know the theta, I measure it by using protractor. So T cos theta, when I resolve vertically, T cos theta, this is horizontal. So when I resolve vertically, this has no vertical component. T cos theta is equal to mg. T cos theta will be equal to mg. So this tension could be T1, something else. We don't need to know that. So T cos theta equal to mg. So from this I can find T equal to mg over cos theta. So the simple answer, they are giving 5 marks, but the answer is simple. First you should say from the attached mass, find the total mass attached. By using weight of force equal mg, find the total vertical downward force. Second mark they are giving. Measure the angle theta by using protractor from the photograph. Then since it's at equilibrium, T cos theta is the vertical component equal to mg. From that find the T. That's all. That's a very simple answer. I think you can write it. You don't need to draw a vector diagram. If you want, you can draw a vector diagram here, but not necessary. You are just finding the T anyway. So calculation is easier than drawing vector diagram again. So it's better find it by using calculation. Okay, question number 17, which is related to momentum. The diagram shows two bumper cars P and Q at an park. Q was stationary, P was moving at a speed of 2.10 meter per second towards Q. So P moving and Q is at rest. P collided with Q. After collision, P and Q moved off in the same direction. P moved with a speed of 1.15 meter per second. Q moved with a speed of 1.57 meter per second. Show that the total mass of Q was about 150 kilogram. Total mass of P is given. So it's actually like a IGCSE question. So we need to use law of conservation of momentum. So A part, we can use the law of conservation of momentum. So we can say it's moving to the right. So I use the law of conservation moment towards right. So the mass of P is 250 kilogram. Mass of P into its velocity. It's moving at 2.10 meter per second before collision. But the Q was at rest. Its mass M, which is at rest, so 0. After collision, the P is moving at a velocity of 1.15 meter per second, so 250 into 1.15. Q is moving at a velocity 1.57. Simple question. So find the M from here. You will get 151.3 kilogram, approximately 150 kilogram. Okay, B part. Second, this is the A part, first part. What I did is A part, first part. A part, second part. State one assumption you made in your calculation. There is no external force. Otherwise, I can't use the law of conservation of momentum. So the assumption is there is no external force. Right. A part, third part, the total collision lasted a total time of 1.35 seconds. Calculate the average horizontal force on Q during the collision. So we know the force exerted by P on Q will be equal to force exerted by Q on P. So for one of it, I can use the change in momentum. So change in momentum of Q is equal to delta P is equal to mv minus mu, is it? So that is equal to F into T. You know that. change in momentum equal mv minus mu, that is equal to impulse of force into time. Equations given in the data sheet. So that means Q was initially at rest. So mass of the Q is 151. So I can find it 151.3 into final velocity. We know that 1.57. It was at rest initially. So initial momentum 0. The force I need to find, the time is 1.35. From that find the F. You will get 176 Newton. That's a force exerted by P on Q. Okay, question 17, the same question, momentum, B part. Explain why P decelerates during the collision. P is the first bumper car which decelerates during the collision. Your answer should make reference to Newton's laws of motion. So here you can see the Q was at rest, and when P hits Q, Q is moving towards right. So P was moving towards right, P was moving towards a stationary car Q. After collision, car Q is moving towards right. That means according to Newton's first law, the car Q is experiencing a resultant force towards right, because object which is at rest is not continuing at rest, means it's experiencing an unbalanced force towards right. That's the reason Q is experiencing an unbalanced force towards right. How it got that force? The force experienced by Q is given by the car P. Now we can use according to Newton's third law. Car P exert force on Q to the right. So according to Newton's third law, car Q will exert force on P to the left. That means the force experienced by the car P from Q, which is towards left, is in opposite to the direction of velocity of the car P. It's experiencing an unbalanced force in opposite to the direction of its velocity. So what will happen? The car P will decelerate due to the unbalanced force which is exerted on it in opposite to the direction of velocity. So it will decelerate, so it will slow down. Okay, question 18 is related to projectile motion. A golfer hit a golf ball into air at a speed of 52 meters per second and at an angle of 41 degree to the horizontal. The diagram is given. The ball landed on the ground near a hole. The ground was 11 meters higher than the starting point of the ball. So vertical displacement, if the ball lands here, is 11 meter upward direction. Show that the vertical component of the ball's initial velocity about 30 meter per second. So that's nothing. So A part, initial vertical velocity, I can say UV, V stands for vertical, 52 sine 41, just nothing. So you will get 34.1 meter per second. So they ask him to show that about 30, so we'll say approximately 30 meter per second. That's nothing. B part, that's A part answer. So B part, show that the time taken by the ball to reach the ground was about 7 seconds. You should ignore the effect of air resistance. So the time taken to reach the hole, that is vertical displacement 11 meter, is about 7 seconds. We have to show that. So we know the vertical displacement. I'll do it here. The vertically S equal ut plus half at squared. So we can use this in vertical direction. So when it reaches the hole, because it's saying it reaches closer to the hole, they are saying it. Ball landed on the ground near a hole, they are saying it in the second paragraph. So the vertical displacement is 11. The initial vertical velocity we found it 34.1. I'm using upward direction, positive, into t plus half into g is downward direction. We are taking upward direction, positive. So minus 9.81 t square. So that's going to be 11 equal 34.1 t minus 4.905 t square. So it's a quadratic equation, 4.905 t square minus 34.1 t plus 11 equal 0. That's a quadratic equation. Okay, solve it by using calculator. So you will get calculator answer. For the time you will get t is equal to 2 answers. You will get it because it's a quadratic equation. You can find it by using calculator. 6.62 seconds or t equal 0.34 seconds. These are the 2 answers. You will get it. Okay, so here we are getting 2 different answers, 6.62 and 0.34. Which one is the time taken to reach the hole? Actually, you know, we took the vertical displacement 11 meters. So when we consider the motion, if I draw the path of the projectile, the path of the ball, it reaches somewhere here means, so it would have gone something like this. So that means here 11 meter at the same level, here also it's passing a point 11 meter. So to reach this point, the time taken is 0.34 seconds. So you know, when the ball reaches the ground, it should come down. It should come down. Its velocity should be downwards. But here the velocity should be upwards because on the way, it passes 11 meter here also. Again, when it comes to the same 11 meter, it hits the ground. So here 0.34 second is the time taken to reach 11 meter before reaching the highest point, because after reaching the highest point only it can go down and land on the ground. When it is moving up, here it can't reach the ground, because if it wants to fall on the ground, it should pass its highest point. So final answer, you should say 0.34 is the, if you want you can say that, but in the mark scheme they are not telling anything about it. They are just accepting if when you say the time taken is 6.62 seconds. But you can say we are 0.34 seconds is the time taken to reach vertical displacement 11 meter before reaches its highest point. Therefore, the time taken to reach the ground is 6.62 seconds. Again, I'll tell that we are 0.34 seconds is the time taken to have a vertical displacement of 11 meters before it reaches the highest point. But when it lands on the ground, it should move downwards after passing the highest point. Therefore, the time taken to reach the ground or time taken to reach the hole is 6.62 seconds, not this answer. You can tell that, but mark scheme they are not expecting that answer. Okay, so the C part, the hole is a horizontal distance 250 meter from the starting point of the ball as shown. They are giving a diagram again. This is 250 meters they are saying this diagram, so I didn't release this one. So this diagram, this distance, they are telling the hole is at a distance of 250 meters from the initial point. You should deduce whether the ball landed within 5 meters of the hole. You should ignore the resistance. So horizontally, so this is answer for C part. Horizontally use S equal ut plus half at square. We neglect the drag force. So horizontally there is no gravitational acceleration, so it will become 0. So horizontal range we will get it. Initial velocity 52 cos 41 into the time taken, we found it already 6.63 seconds, 6.63 seconds, 625 actually earlier I got, so 6.63 seconds plus half into no acceleration in horizontal direction. So solve it, you will get The horizontal displacement 260.3 meters, 60.2 meters. So the distance from the point where it hits the ground and from the initial, so the D, the distance between the hole and the point where it hits, if I say D, the distance between the point where it hits the ground and the hole is 250 meter from the initial point, it's landing at 260 meter from the initial point, so D is the distance between the point where it hits the ground and the hole. D is given by 260.2 minus 250, that will be 10.2 meters, which is greater than 5 meter. So the ball will not hit within 5 meters from the hole. Okay, question 19. A falling sphere viscometer is a device used to determine the viscosity of a liquid. A sphere falls through a cylinder containing a liquid and the terminal velocity of the sphere is measured. State A part, question number 19, A part. State why the temperature of the liquid should not increase during the measurement. So you know, when the temperature changes, viscosity of the liquid will change. So we can say when first part answer, question number 19A part, you can say viscosity decreases with increase in temperature. Viscosity of liquid decreases with the increase of temperature. Right. B part. A scientist measured the terminal velocity of an aluminium sphere as it fell through a glycerol, showed that the weight of the sphere is about 4.8 10 to the power minus 3 Newton, density of the aluminium 2.70 10 to the power 3 kilogram per meter cube, diameter is given as 7 into 10 to the power 3. So weight we need to find it. So density given, diameter given, we need to find the weight. So question number 19, B part, first part, the weight is equal to 4 by 3 pi r cube rho j. 4 by 3 pi, the radius is diameter given as 7 into 10 to the power minus 3. So radius will be 7 into 10 to the power minus 3 divided by 2 all the cube into density of the aluminium given 2.70 10 to the power 3 into 9.81 Newton. So the answer will be 4.76 10 to the power minus 3 Newton, approximately 4.8 10 to the power minus 3 Newton. Okay, so that's the answer for B part, first part. B part, second part. The terminal velocity of the sphere was 4.05 10 to the power minus 2 meter per second. Deduce whether Stokes' law applied to the falling sphere. You know the condition to use Stokes' law. Two conditions. First condition, the fluid flow around it should be laminar. Second one, we can use Stokes' law only for spherical shape objects. Okay, so two conditions. It should be a sphere. Second one, the flow of fluid around the sphere must be laminar. Otherwise, we can't use the Stokes' law. Density of the glycerol is given. Viscosity of the glycerol also given. So we need to find the, decide whether the Stokes' law is applicable. Okay, so when the sphere falls down, there will be three forces acting on the sphere: downwards, weight; upwards, upthrust; and upwards there will be drag force. So at the terminal speed, the resultant force must be equal to 0. All the forces should balance each other. So I can see at terminal speed, the resultant force, which is downwards, F is equal to mg minus u minus fd must be equal to 0. So resultant force must be 0 at terminal speed. So we know the weight, already we found it, that is 4.76 10 to the power minus 3, we already found that. So substitute here 4.73 10 to the power minus 3. Upthrust we need to find it. You know upthrust is equal to weight of the displaced fluid according to Archimedes principle. So 4 by 3 pi r cube density of the liquid into G is the upthrust should be equal to drag force. We substitute the values 4.73 10 to the power minus 3 minus 4 by 3 pi. The radius of the sphere will be the same as the radius of the the volume of the sphere is same as the volume of the liquid displaced, so that will be same radius 7 into 10 to the power minus 3 by 2 all the cube. Density of the liquid is given, or glycerol given 1.26 10 to the power 3 into 9.81 is equal to the drag force. So we find the drag force. How much will be the drag force at terminal speed when it reaches the terminal speed? What could be the drag force? That is equal to 2.54 10 to the power minus 3 Newton. Okay, so that's a drag force. But I did not use the Stokes law here. Without using Stokes law, I just use the condition for equilibrium, because when it reaches the terminal speed, all the forces should balance. I found the terminals. I found the drag force by using the condition for equilibrium, which is the resultant force equal to 0. I didn't use the Stokes law. Right, now I'll use the Stokes law and check what could be the drag force at this particular speed. The speed of the ball, the sphere is given 4.05 10 to the power minus 2. So I can say if Stokes law is applicable, the drag force will be equal to 6 pi eta RV. So 6 pi. The viscosity is given glycerol 9.50 10 to the power minus 1 6 pi eta. The radius will be 7 into 10 to the minus 3, half of it, so 3.5 10 to the power minus 3, that's a radius, into the terminal speed is given 4.05 10 to the power minus 2 meter per, minus 2 Newton. Solve it. You will get exactly the same answer, 2.54 10 to the power minus 3 Newton. Same answer you will get it. That means we can use Stokes law. Stokes law is applicable because the required drag force, which is under the condition of equilibrium, is same as the drag force provided by the Stokes law. Both have the same numerical value, means Stokes law is applicable in this situation. So you have to give that conclusion. I am not writing it. You must write Stokes law is applicable. You must write it here. Stokes law is applicable. Okay, the last part of this paper, question number 19, part C. A scientist used a viscometer to measure the viscosity of blood. The viscosity of blood is typically in the range 3 to 10 to the power minus 3 Pascal second to 4 into 10 to the minus 3. You know that viscosity, when you compare with the glycerol, is much smaller, much lower than viscosity of glycerol, is it? Explain why the scientist should use an aluminium sphere. Early experiment also they use aluminium sphere, but here aluminium sphere with much smaller diameter than the sphere used with the glycerol. Do not include calculations in your answer. Viscosity of the glycerol, again they are reminding you 9.50 10 to the power minus 1 Pascal. So why should we use much smaller sphere in this experiment where we are trying to find the viscosity of blood, which is much smaller than glycerol? Okay, if you are using Stokes law, so in this experiment to find the coefficient of viscosity, we have to use the Stokes law at terminal speed. Yeah, we will use the total upward force equal to total downward force. Only thing we need to measure the terminal speed. So in this experiment, we measure the terminal speed. Normally in the laboratory at schools, what we do, we use a taller tube and we put two rubber bands here and we fill it with glycerol and we drop the ball bearing and we measure the distance between the two mark or two rubber bands. So we know the distance and it's a glycerol which is transparent. We assume before it reaches the first rubber band, the ball bearing reaches terminal speed. So we measure the time taken by the ball bearing move from the first rubber band to the second rubber band or first marker to the second mark. We measure the time by using stopwatch at eye level. Then we divide the distance between the two marks by the stopwatch reading. We find the terminal speed. So we assume it has reached the terminal speed. Then we say we measure the diameter of the ball bearing by using micrometer screw gauge. We know the density of the material of the ball bearing. So the weight, everything we know. So we say that the total upward force is equal to total downward force. So when the ball bearing move downwards, total upward force will be up thrust and the drag force is equal to total weight of the ball bearing. So the up thrust we know we can find it by using the volume of the sphere. We know the density of the liquid, mostly use glycerol, we know the density, so we know the up thrust. So up thrust is known quantity. FD we can use Stokes law. Here you have to use the Stokes law. 6 pi eta RV. V we found it distance over time taken. The distance between the two markers divided by the time is the speed. And weight of the ball bearing we can weigh it on a weighing scale. We know the weight of the ball bearing. So from this everything we know. Mg we know, radius we know, terminal speed we know, up thrust we can calculate by using the volume of the ball bearing and the density of the glycerol. So we find the coefficient of viscosity, right? So here you have to use the Stokes law, but the condition to use Stokes law, when the ball bearing moves through the liquid, the flow around it must be laminar. It should not be turbulent, because if it becomes turbulent, the Stokes law cannot be used. The turbulent flow occurs at higher speed. So here the problem is the terminal speed should be smaller. Terminal speed must be a smaller quantity, possibly smaller quantity. So if it is smaller quantity, the fluid flow around it will be laminar. So how can we achieve lower terminal speed? When it falls down, it should balance. The forces must be balanced. Total upward force must be equal to the weight. But here what happens? We know the drag force is going to be smaller for a particular speed. At a particular speed, the drag force is going to be smaller when we are using blood, because the viscosity is smaller. So when the viscosity is smaller means what happens? To balance the weight for a particular weight, the speed should become larger. When the speed becomes larger to balance the particular weight, what can happen? There could be a turbulent flow, where we can't use the Stokes law. So what should we do? We should reduce the weight of the ball bearing. By reducing the weight of the ball bearing, for the aluminium, the density is constant. By reducing the radius of the ball bearing, we can reduce the weight. When we reduce the weight, this quantity can easily balance the weight even at lower terminal speed. Understand? So we can balance this quantity. We should reduce this weight. By reducing the weight, how can we reduce the weight? Reduce the radius of the sphere. By reducing the radius, we can reduce the weight. When we reduce the weight, even at lower speed, we will be able to balance the total downward force by the upward force. So if we can balance it at lower speed, means the terminal speed could be smaller, there it won't be a turbulent flow, it will be a laminar flow. That's the answer you should give in this question. Okay, so I hope you understood the answers for May, June 2022, Unit 1 IAL paper. So if possible, I will discuss other IAL Unit 1 papers also. Bye.